Electricity is absolutely incredible, right? But here's the thing. Its usefulness comes entirely from one single fact: our ability to control it. Without control, electrical energy is just raw, chaotic power, kind of like a lightning bolt. But because we can control its flow, we can power everything from the smartphone in your hand to entire bustling cities.
So it brings us to a really fascinating question. How exactly do we force wild electricity to go exactly where we want it? We know raw electricity is powerful and, frankly, quite dangerous. To harness it safely, to make it turn on a lamp or boot up a computer without harming us, we rely on a very specific set of materials.
Okay, let's dive into this. Here is our roadmap for today's explainer. First, electricity's highways and walls. Then, conductors, letting current flow, followed by insulators, stopping the flow. After that, we'll see how the secret is electrons, talk about testing materials yourself, and wrap up with real-world electrical safety.
Section 1. Electricity's highways and walls, the great dichotomy of materials.
Section 2. Conductors, letting current flow.
In the world of electrical physics, everything basically falls into one of two camps: impenetrable walls or massive expressways. Let's start with the expressways. By definition, a conductor is a material that actively allows electric current to flow right through it. When you think of conductors, your mind should immediately jump to metals. They are literally the quintessential pathways for electrical energy happily taking the current and passing it along down the line.
What's really fascinating is the sheer scale at which conductors operate. Think about heavy-duty overhead wires spanning hundreds of kilometers against the sunset. They rely on aluminum or steel, mostly because those metals are cheaper than copper, yet they still conduct beautifully. Meanwhile, the printed circuit board inside your laptop uses tiny, microscopic copper tracks to conduct current. Whether it's a massive power grid or a tiny microchip, conductors are the vital highways. But, a highway isn't really safe without guardrails.
Which brings us to Section 3, insulators, stopping the flow.
Now we must pivot to the exact opposite type of material, which is absolutely essential for containing all that raw power. An electrical insulator is a material that does not allow electric current to flow through it. If metals are our conductors, most nonmetals are our insulators. Prime everyday examples include plastic, wood, air, and cotton. These materials boldly stand in the way of electrical current and just flat out refuse to let it pass. They inhibit the flow completely.
And thank goodness they do. When you safely grip a power plug, you're relying on plastic, a fantastic insulator. Because of that plastic, you can push the metal pins into a live socket without the current flowing into your hand. The wire trailing away is also coated in plastic to protect people from electric shocks. Insulators are our physical protectors. They're the walls that keep the electricity safely inside the conductor.
Section 4. The secret is electrons. What's happening at the subatomic level?
We've looked at the macro world of wires and plugs, so the crucial point is this atomic structure comparison. In conductors, electrons are free to move. When a current is applied, those free electrons eagerly jump from atom to atom, passing the electrical charge along. But in insulators, the electrons are not free to move. They are stubbornly locked in place around their atoms. No matter how much the current pushes, those electrons simply won't budge, which means the electrical energy cannot travel through the material. It's an elegant, invisible atomic dance that dictates the rules of our visible world.
Okay, Section 5. Testing materials yourself. Conduct or insulate. It's time to shift from abstract theory into something you can actually test. How do we definitively know if something is a conductor or an insulator? Well, with a basic testing circuit. We use a battery cell to provide the energy, wires acting as our conductors, a lamp to serve as a visual indicator, and 2 crocodile clips with a gap between them. Now, there is a massive safety rule to remember here. You must never connect a conductor directly across the terminals of a cell or battery without a component like a lamp in the circuit. If you do that, you create a short circuit, which can dangerously overheat the wires or totally damage the battery. The lamp provides necessary resistance while letting us test our materials safely.
The scientific procedure is wonderfully straightforward. You simply set up your circuit with that gap between the clips, attach the material you want to test, and watch the lamp. If it lights up, boom, the material has completed the circuit. It's a conductor, letting the electrons flow. If the lamp stays dark, the material is an insulator, stopping the electrons right in their tracks.
You can test all sorts of everyday household objects with this setup. Imagine putting a piece of paper between those clips.
The lamp stays dark, right? Because paper is wood-based, making it an insulator. What about a plastic pen or a ruler? Also dark. But what about metal house keys? The moment those clips touch the metal, the lamp bursts into light, because the keys provide a massive highway for the free electrons. It's just a brilliant way to visually prove subatomic physics.
Section 6. Real-world electrical safety. Protecting ourselves from extreme energy.
We've tested small batteries, but these exact same principles are applied to keep the public safe on a massive industrial scale, and this brilliantly illustrates the real-world stakes. Consider a towering metal power pylon. You have high-voltage wires carrying immense electrical current, but the pylon tower itself is made of metal, which we know is a conductor. To prevent an absolute disaster, engineers use heavy-duty insulators, those large disc-like structures you'll see holding up the wires. They sit directly between the live conducting wires and the metal pylon.
Just think about what would happen if we didn't have those insulators. If the live wires just rested directly on the metal towers, the current would flow straight into the metal pylon. The electrical energy would instantly dissipate down into the ground. Our power grids would simply fail to deliver electricity to our cities. And even worse, the metal pylons would become highly electrified, and anyone or any animal touching them would get a severe electric shock. Insulators truly are the silent heroes of the power grid.
If you take away just one thing from this explainer today, let it be this fundamental law of physics. Conductors allow electrons to flow. Insulators inhibit electron flow. This perfectly balanced relationship between letting energy move freely and forcing it to stop is the entire foundation upon which we build our modern technological world.
I'll leave you with this thought. We're demanding more and more electrical power every single day for our cars, our homes, and our incredible technologies. So as we push the boundaries of energy, how will our reliance on these perfectly balanced conductors and insulators evolve next? Will we discover new materials that totally redefine the boundaries of free electrons? It's a thrilling frontier. Thank you so much for exploring this fascinating topic with me today.